Hi there! Thanks for clicking into this video of our Structure Meta series. I see you're curious about binding affinity and technologies that characterize it, right? Let's learn something about it today. By the way, my name is Maria Ma. I'm the Application Scientist and Market Development Manager at RedShiftBio.
All right, let's move on to the slides. So currently, the most common technologies that characterize binding affinity are SPR, BLI, and ITC. I know, three-letter acronyms, but don't worry, I will get to each of them. But before I go there, let's talk about binding affinity first. For a drug to be functional, it has to bind to the target molecule first. The nature of such binding and de-association is known as the affinity. Efficacy, on the other hand, is a measure of the action of a drug once binding has occurred. Like the diagram on the right, a drug has no affinity is no use. An antagonist is expected to have high affinity yet no efficacy, while other types of drugs need both high affinity and high efficacy. So affinity and efficacy together will describe how the drug will function. The function is determined by the structure of the molecule. Once we have selected the optimal candidate that has the perfect affinity and efficacy, we will need to make sure that the molecule maintains a stable structure to be stable in function, and then we will have a good product. So we really can't and shouldn't downplay structure, and that is why we're making this Structure Meta series. Now let's talk about the technologies that characterize affinity, and let's start with SPR, which stands for Surface Plasmon Resonance. The surface is a planar metal, for example, gold or silver. Although it is called a surface, it is still three-dimensional, of course. Nevertheless, we can assume it behaves like a 2D surface. And this is because the planar metal is made up of an electron sea. We assume all electrons in the sea behave like the same electron. So whatever happens on one side of the metal also happen on the other side. So from now on, I highly recommend that you turn on the CC below for better understanding if you're not familiar with this topic. Here on the right side of the metal, we have linked a binding molecule, for example, a conjugated antigen. When there's a flow of analytes, for example, antibodies come and bind to this antigen. It affects the oscillation of the electrons. Since the oscillation of the electrons triggers electromagnetic waves, which is light, we can then probe the light or photons on the other side of the metal to monitor the binding activity on the other side. In the case of SPR, the incident light has a single wavelength with a fixed angle. Then a prism is used to broaden its incident angle. Among the reflected light, there is a blacked out angle, which is due to the absorption. This angle will shift when there is a binding event. We use resonance or response unit, or RU, to describe this angle shift. Specifically, 1 RU is equivalent to a critical angle shift of 10 to the -4 degree. Then we plot the RU, the resonance unit, against time. The RU increases when more molecules bind and then decreases when they de-associate. Now we can get the K on and K off and then calculate the big KD, which is the equilibrium de-association constant. So that is all for SPR. The next one, BLI, stands for Biolayer Interferometry. The fundamental idea of BLI is so similar to SPR that I don't even need to change the figure here. The only difference is that instead of using a single wavelength, and measuring the angle shift. BLI uses a white light source and measures the wave number shift. This may result in differences in sensitivity and price, of course. And now let's talk about ITC, which stands for Isothermal Titration Calorimetry. This is a traditional technology that has got quite a history, yet it still constantly proves its value and importance today. It's completely different from SPR and BLI as it's based on calorimetry. When, for example, the antigen and antibody are added into the reactor, there will be a heat released or absorbed until the system reaches equilibrium. Since it's isothermal, the reactor is trying to keep the temperature the same. So in this figure below, the red curve records the enthalpy changes during this process until the binding and deassociation reaches equilibrium. From this curve, we can get the equilibrium deassociation constant, the big KD, the net enthalpy changes, and the stoichiometry of the reaction. So here in this table, we compare these three different technologies. SPR, BLI, and SPR and BLI are very high throughput technologies, while ITC is very low throughput. The sensitivity of SPR is usually high. BLI sensitivity ranges from low to high. The sensitivity of ITC really depends on the net enthalpy of the reaction. So the next two rows in the table describes the amount of molecules needed for the measurement. The values here may not be very accurate as there are so many different instruments out there, but overall you see that SPR and BLI needs way less sample than ITC. The number of samples you can run in a single setup on SPR and BLI are hundreds, if not thousands, and it can be scheduled to be run for days. ITC, on the other hand, although it has been improved in the recent years, it's still a really low throughput technology compared to SPR and BLI. So the data output of SPR and BLI are the same, the K on and K off. Then you calculate the big KD. ITC only gives the big KD without K on and K off, but it quantifies the stoichiometry and enthalpy, which cannot be achieved by SPR and BLI. So ITC acts as an orthogonal technology to SPR and BLI, as it measures the same big KD from a completely different way. In fact, using orthogonal technologies is requested by FDA. So now it leads to the next question: when and why do we use them respectively? So first, when and why do we use SPR or BLI? The answer is in early discovery phase. So biopharma companies usually have an important group dedicated to binding affinity screening, because there's nothing we can talk about if you don't bind well, you as the candidate molecule. Since in early discovery, there are usually so many molecule candidates to be screened through that a high throughput technology is a must. So SPR or BLI is essential here. ITC, on the other hand, won't be here as it's low throughput and requires much greater amount of molecules. So why do we still bother with ITC? As I previously mentioned, ITC acts as an orthogonal technology to SPR or BLI, as it measures exactly the same KD from a completely different way. FDA suggests that whatever we measure, we should use an orthogonal method to check it. as no instrument or no technology is perfect. Although discovery folks won't bother with ITC, some candidate molecules might be handed to analytical support or contract services to check with ITC results. As far as further down the development pipeline, Affinity might be characterized with ITC to study the effect of different formulations, processes, and manufacture changes. Apart from being orthogonal to SPR or BLI, ITC can also give additional information on the net enthalpy changes and stoichiometry of a certain reaction, which cannot be achieved with SPR or BLI. So that is all. Thank you for sticking to the end of the video. I really hoped you learned something new today. And if you have any questions, please feel free to shoot me an email. And also, please consider giving us a thumbs up. Thank you.